All right, in this next segment, we'll talk about inverse distance weighted sampling routines. And you can find these in a variety of places, one of them being in spatial analyst tools under interpolation. You can go to IDW. So IDW is it's a similar concept to the bilinear convolution, or sorry, the bilinear interpolation and the cubic convolution interpolation. What inverse distance weighted does is it estimates the value for location as the weighted average of nearby data values within the roving window. I guess that what you could think of both bilinear and cubic as specific examples of inverse distance weighted, in which the number of points that you use, or the window, is defined. So with in the case of bilinear, it was the 4 nearest points, and in the case of cubic convolution, it's the 16. Now, inverse distance weighting is a little bit more generic, and you can use a number of points, or you can use a distance from the location that's being estimated. There's a couple different ways to do it. So if I have this example here, this is actually out of your book, where this is the point that I want to interpolate at. Say that's the center of a grid cell. What I would do is I would take, in this example, let's say that these all fall within some distance, some radius, some window around me. And so in this case, I'm going to take these distances. That's 4 away. This is 2 units away. This is 6 units away. And then I take the actual values at each of these points, right? And so I take the values and I divide by those distances and add them up. And then I divide again by 1 over each of those distances. And that's where the inverse distance comes from, because the inverse of the distance is 1 over it. And then I end up with this value. So here I got 30, 50, and 52, and shoving it into this equation, it's 34. And so this search radius is key, and it can be based on a distance, it can be based on number of cells, or it can be based on a count. So here it looks like 1, 2, 3, 4, 5 is the count. Here obviously 3 was the count. And with bilinear, the count is 4. Cubic convolution, the count is 16. So you have these different parameters, right? So n in this equation is, that exponent. And what this does is it sort of sets the influence of that point as it gets further and further away. And so if in the first example we just ran that with a exponent of 1, but you could have that exponent be something else. So in these two, the exponent is 2. And then I controls how many points around you that you use, right? And so in this case, we're using 6, 6, and 20. So this is the original surface from which these points are extracted off of it. You take those points and you do an inverse distance weighting routine, and you keep the exponent of 1 and use the 6 closest points around you. This is what you get. Now, if you still use the 6 closest points around you, but you change that sort of weighting of the influence as the point gets away, this is what you get, right? And so we can see that this one's a little more nuanced and this one's a little bit smoother by adding that exponent in. Keeping that exponent at 2 and then adding more points around you, you can see this is what you get. So these are the knobs, if you will, that you get to control in an inverse distance weighting routine. And so in ARC, you can go in and run the IDW, and you tell it what are the input point features you want to use. So there's your points. Which value field in the points has the values that you want to interpolate. Where's the raster? And then these are those 2 knobs. So the output cell size, oh sorry, not those 2 knobs, it's this one and this one. Output cell size is obviously the resolution of your raster. The power, this is if you want to, this is the exponent. So if you leave it blank, the power is just 1. Or you could use an exponent of whatever you decide. And then you have choices for the search radius. And variable search radius allows you to specify a number of points. So it doesn't matter how far apart they are, it's just going to find the 12 closest in this example, or whatever number you specify, versus fixed you would specify the distance, and then it would include distances within some radians. You can input barriers so that you could think of these sort of analogous to break lines. We talked about break lines in the context of tins, and they would keep you from sampling stuff on the other side of a barrier. So if you were using IDW and you had a cliff, you wouldn't want to use the 10 closest points for stuff on the other side of that cliff. So this is a way to basically use a break line, if you will. So here's what IDW looks like if we just shove in the points that we have. And it kind of looks bizarre, right? Some sort of Martian topography. Now, don't take that as this is not a good interpolation scheme. This is, what I got here is entirely dependent on those two parameters I used, the search radius and the power. And so I could get a very different looking thing, something that looked closer to our tin interpolation if I played with those knobs. But if I just use the defaults, this is what you get out of that. So next we'll talk about spline, and we'll move on.